By the end of today's video, you'll understand what a fiduciary tag is, like an AprilTag, and how you can track one of them using a simple camera object. We can see how far away we are, which at this point is about 24.8. I'm Brogan Pratt, and I've been teaching robotics and design for over a decade now. And today we're going to use the HuskyLens AI machine learning camera to be able to read fiduciary sensors. I'll show you how to wire and program and plug one of these things into a CircuitPython board so you can get it programmed up in Python. And then I'll also tell you how you can recognize up to 6 different tags and be able to measure distances away from these tags accurately. What exactly is a fiduciary tag? And by a fiduciary tag, what is an AprilTag? So an AprilTag is this little grid here. It's an 8x8 square grid. And it is effectively kind of like a QR code for robotics, but it has less information in it. Now with a QR code, you have really dense images. Problem with really dense images with small camera sensors, it can be really hard to be able to tell the difference between where one pixel starts and one pixel ends. So by actually having less data inside of one of these tags, we actually end up getting more data. And this is an AprilTag because it's developed out of the April department from the University of Michigan and the robotics lab down there. There are different tags and different families that exist. This is from tag family 36H11, and different families have different distances you can measure them away from because there's more or less data inside of them as well. And effectively, what an AprilTag lets us do is every single AprilTag that is ID 20, this family here, I believe, has 400 different tags inside of it. And each individual tag is always going to look like this. So ID 20 will always look like this. ID 21 will always look like something else. So it allows us to have a common reference point for robotics to be able to look at these tags and say, okay, I know I'm looking at ID 20. And because they all have fixed sizes, this image here is 200 millimeters by 200 millimeters across. Because you know the fixed size of this and you know the fixed size in your camera, you can use some inverse square laws to be able to do a calculation to say, okay, if the image is this big on my screen, then the image is this big. We know how far away we must be. AprilTags are super useful in robotics because it allows you to do different things like localization. Things like you could set up a field with 4 AprilTags in each corner of the room, and depending on where you look at that AprilTag, you can know how far you're away from a specific wall inside of the room. You could even have specific tasks set up, like you could have put up AprilTags around your warehouse. You could have AprilTag 1 is where you're going to be dropping off an object. AprilTag 2 is where you're going to be picking up an object from. And AprilTags 3, 4, 5, and 6 are waypoints along the way to be able to get yourself to there. So it can be really useful for localizing your robot around space. So let's talk quick about what the HuskyLens is. It is a AI machine vision sensor. It's got 7 different functions in it. It can do face recognition, object tracking, object recognition, line tracking, color recognition, tag recognition in terms of AprilTags, and object classification. So it's a pretty cool little piece of sensor. You got the actual camera right here. You have a function button, which is kind of like a little toggle switch that you can then impress and also rotate. You have a main function button over here. You have a 320 by 240 pixel screen on the back. You have communication here by either UART or I2C. You've got a micro SD card slot for loading programs. It's also got a micro USB cable that can provide power into it. And then it has a couple different standard LEDs here, or LEDs, for making your image a little more consistent. Up at the top, you have an RGB LED that you can use as an indicator, or it also uses for different learning aspects as well. When it comes to wiring one of these up, it's going to be super simple. We've got our Metro M4 Express, or any other CircuitPython board. You can use this on a Raspberry Pi, would work just fine. And then we are going to be connecting down here to these ports. We have our T, our R, minus and plus for our power and ground. So I'm going to grab this HuskyLens connector here. We're going to go ahead and plug this in. And in our case, T is going to refer to green, R is going to be blue, and T, because we're going to use I2C for this tutorial, T actually ends up becoming your SDA or your data line. And blue, or R, ends up becoming your clock line. So as far as wiring this thing up, it's quite simple. It comes down to a couple different male jumper wires here. Red is, of course, our power. You need to provide 5-volt power to this. So we're going to find our 5-volt power up over here. We'll connect it to power and ground at the same time because of the way that I've wired that up. And then over here with this green and this blue, green is our data line and blue is our clock line. So up here on our Metro board, we have our SCL and our SDA for clock and data respectively. So I make sure that I plug the green wire into data and the blue wire into clock. So we'll flip that around. And you're now powered up, so you should be able to connect this to your computer or the Metro board to your computer with a micro USB cable. And provided you have that done correctly, the HuskyLens should wake up and it should be started up in our main modes here. So the first thing I do is I need to make sure that I'm actually inside tag recognition motion. So of the two buttons up here, I'm going to go ahead and press the learning button. I'm going to rotate over until I find tag recognition. And inside tag recognition, I'm also going to push and hold the button so we can get into our settings. And I'm in the learn multiple. And on learn multiple, I'm going to push and hold. I'm going to make sure that I flick this on so we are capable of learning multiples. Click down to be able to save, and then I'm going to click and save here, and then yes, we will save our data. So now we're ready to actually start learning. On my page here, I have two different AprilTags. I have tag ID 0 and I have tag ID 3. So they're clearly two different sizes. You make sure they're facing up here. And now we're capable of learning both. On the HuskyLens, you can see on the bottom here, I've got an orange and yellow flashing circle. That means we're ready to learn our tags. So what I'm going to do is I'm going to have that little crosshair hover over top of a tag, and we should see that there should be a nice white square showing up around our tag. When it's recognized, and then if we move over, we can have another white square showing up in the other one. So to be able to recognize both of these, what I'm going to do is I'm going to hover that crosshair over one of them, press the learn button, then we can go over and press the learn button again to be able to learn a new tag. And when I'm done learning all my tags, I can recognize up to 6, then I can just simply let the countdown timeout. So I'm going to press 1, notice it recognizes, I'm going to come again, I'm going to click another button within those 5 seconds, click another button, and then we should be ready to just let this countdown roll down. And now we have recognizing tag ID 1 and tag ID 2. And then we can actually see we can have both of them up on our screen. Now recognize that with these tag IDs, the tag ID is the number in which the HuskyLens has learned it. It is not to do with the actual AprilTag itself. So in our case, ID 0 is actually tag ID 1, and ID 3 for AprilTags is actually tag ID 2. So we want to make sure we do that. So I'm going to go ahead and forget these. So I'm going to go ahead and click up to forget. Because for this tutorial, I'm not using 100mm square AprilTags. I'm using 200mm square AprilTags. I'm using ID 20 for this. So I'm going to be able to hover out, click on the learn, and then now we have tag ID 1. So now that we've recognized an AprilTag, we can actually go ahead and start doing some things like that. So let's go over to our code now. Now, my favorite editor to use for this is the Moo editor. And then for CircuitPython, you have to make sure that on your CircuitPy drive, underneath the lib folder, that you have the following file in there, CircuitPy huskylib.py. I'll have a link to that in the description down below. If you don't have it on there, this isn't going to work for you. So now let's actually get back our information. First thing we're going to do is we're going to import board and import time. And these are just some simple libraries that allow us to be able to access different pins as well as access the board. I'm going to say from CircuitPy huskylib import the HuskyLens library. And that is actually going to import in that HuskyLens Python file that we put in for you down below. We're going to create a new object for HuskyLens. So I'm going to say that HL, this could realistically be anything you want. It could be Husky_lens. I'm a lazy programmer, so I like to have a short form here. So I'm going to say HL is equal to our HuskyLens library. And this is going to be I2C as a communication. And our SDA is equal to our board.SDA port. And our SCL is equal to our board.scl port, because we're going to be using the I2C communication for this. Now, when I'm using the HuskyLens here, I like to add in a small little time.sleep at the start of my program just to verify that HuskyLens actually gets connected, because sometimes I have found that you need to give the lens a bit of time to get connected effectively, especially if you're booting this up off an external power supply. Then it's time to switch up our tag or switch up our algorithm. I'll write in hl.algorithm, and inside my parentheses in all capitals, it's going to be algorithm underscore tag underscore recognition. And now we're actually ready to do our main loop. So I'm going to say while true, we're going to create something called result is going to be equal to hl.learnedBlocks. And what the learnedBlocks method is going to return is going to give you back a list of objects of all the different AprilTags that it has seen that it is currently learned. Not just all of the tags that it's seeing, but the ones that it has learned. So it can return up to a list that's about 6 options or 6 units long. And then if there are results, that means if we have detected something, I'm going to loop through all of the results that I have. So I'm going to say for block in results. And then we're going to put in some print statements so we can see what our actual results are. So we're going to print what our block ID is. That could be ID 1, 2, 3, 4, 5, 6. The X value, where it is on that Husky lens. So for example, we know that this Husky lens here is 320 pixels wide by 240 pixels tall. So if it were 0, 0, that would mean the center of the AprilTag is in the 0 top left corner. If the tag is returning 160 and 120, that means it's directly in the middle. And if it's returning 320 and 240, it means in the bottom right. So depending on where it is, we actually end up seeing this tag and this tag ID from. This will show up where our X and our Y values are. Now, the width and the height are, again, of course, the width and the height of that block or that blue or yellow or orange or whatever tag you end up having around the outside of your screen there. And then outside of the loop, I'm going to put in a quick sleep, time.sleep for 1 second, just so we can have these things not totally iterate over. So I'm going to go ahead and save this over to our code.py file or CircuitPy. We'll go ahead and open up the serial port. And let's take a look at, as I zoom in here, we should be able to see our tag. Oops, slides don't cover it up. Since we on the Husky lens here, we've got tag ID 1. And then we can also see on our serial port, I'm going to move the serial port out of the way a little bit. We can start seeing we're actually getting some of our information popping up. So we have ID 1. Right now, it's directly in the center of our X is at 184 and 132. If I were to move it over to the side, we end up with a less X towards the center. Move to the other side, we end up with a greater X towards. If we get closer to the camera, you can see that our width and our height is increasing. If we get further away, our width and our height is decreasing. Now, sometimes it might be useful for us to actually be able to rename those tags because we know that the tag we're looking at isn't actually ID 1. It's actually AprilTag 20. So we can do that by using hl.setCustomName. And inside this, for the first one argument, we can put in a custom name. So I might call this one April 20 with a space after. And inside our comma, we can put in a 2-digit number for the actual ID that it has recognized. So now if we were to save this over and we look at our output for our board here. So as I save this over, rather than saying tag 1, it now says April 20 and then ID 1 after. So that can also help keeping things a little bit more organized, especially when the IDs learned are just the sequential IDs. So the last thing we can do is we can also measure distance from our target. And the way that we've done that is simply with a bit of a brute force setup. So what I've done is with a 200 meter by 200 meter AprilTag, you can realistically measure things from 35 centimeters away all the way up to about 240 centimeters away. So you can get a pretty large distance from how far away you are from that camera and still get a pretty accurate and reliable result. And I put the AprilTag at 34 centimeters away from the camera, and then I measured how large the area was. I put it away at 50, and I measured how long the area was. I measured at 100, how far the area was, and so on, and every single point at 50 centimeter points. Then we can log that data down on a Y table, put it into a power curve equation, and effectively what can happen is as images come towards a camera, the further away it is, the smaller it gets on a square value. So we can actually curve that in sort of in a power law curve to be able to get up what's called an exponent or a different scale that we can have for our equation. Now, thankfully, I've already done a lot of that math for you using a 200-200, but if you want to recreate this using a different size tag, you're welcome to do so. I recommend with the Husky lens, you use a much bigger tag because things like 100 by 100, you're really only going to be from about 17 centimeters up to 100 centimeters. Whereas with this one, even about 35 centimeters up to almost 240. And if you have bigger AprilTags, of course, you can look at things even farther. Now, something else to note about this distance is that the closer you get, the more accurate you're going to be. The further away you get, the less accurate you're going to be. Because the Husky lens can add a lot of distortion inside of its lens because its pixel area is quite small, being that it's only 320 by 240. So the further away you are, the less accurate your results are going to be. We're going to add in a new import, and we're going to say, from math, import square root. And above our while true loop here, we're going to add in a new function. And we're going to call this one define get_distance. And we're going to have to pass in two arguments. We're going to have to pass in the current width of the object and the height of the block that it is that we've grabbed. Now, one last caveat with this as well. You're really only going to have the most accurate results when you're straight on to the AprilTag. If you're at an angle, your square is going to be overlarged because it's not going to be directly looking at it. So you will also drop some of your accuracy a little bit in that respect. So you want to make sure that X value is about 120 for that center X on the tag that you're actually reading if you want to get the best and most accurate distance. So for a 200 millimeter squared tag, we're going to set our scale value. It's going to be equal to, I have 288,000, 2,882,000, and then 190 is going to be our scale value. And then I also find that I have to multiply this by a certain value. And you can add a multiplier here, either greater or less great, depending on how absolutely accurate you want to be. And if you want to have more accuracy at the front or more accuracy at the back. So you can tune this scale a little bit. So tune this scale value depending on your Husky lens itself. And then we'd have an exponent. And for mine, it was 2.045 was a good scaled exponent. Then we have to grab our current tag area. So our tag underscore area. So the area of the AprilTag that we've just grabbed is going to be width multiplied by our height. And then our distance is equal to our scale divided by our tag underscore area. And then has an exponent of 1 divided by our main point there, or our exponent above. The last thing we have to do is simply return our distance value. And if you want to, you're also welcome to round this distance by 2 digits or by 1 digit if you want to have a little bit more accurate, or not more accurate, but if you want to have less data coming back to you. Oops. And then for A here, I actually wrote scale, my mistake. So now when it comes to actually do this, what we can do is we can actually print our distance away from this. So we're going to grab our results like we did before. And then we are going to simply print. We'll say that our distance in centimeters is going to be equal to our get underscore distance. Oops, I need to put a comma in there. So get underscore distance. And we're going to have to pass in our block dot width and our block dot height for that. And we'll go ahead and finish that off. And now as we save this over, we can go ahead and look at the C report. Oh, I'm getting invalid syntax on line 17 because I forgot to say tag area is equal to width times height. Let's go ahead and save that one more time. And we should start getting some tag values with no object tag because nothing's there. So let's go ahead and let's actually take a look at our tag value here. And as we come up and actually look at our tag, and now as we recognize our tag here, if I get my finger out of the way, we can see how far away we are, which at this point is about 24.8. I'm looking at this tag at a bit of an angle, so it's actually going to think that we are closer to this object than we actually are. So I hope you found that a useful tutorial on using AprilTags in your robotics projects. If you'd like access to more code snippets, CAD files, more robotics tutorials, things like that, you can consider joining my community down below. Otherwise, best of luck on your next robotics project.